Welcome everyone to this set of videos which are meant for Nanofraser users, and these specific videos also for people who are interested in knowing some more information regarding the Nanofraser. This set of videos will be mostly useful if you want to get started using the Nanofraser, so we will introduce you with many functionalities and basic setup and use of the Nanofraser tool, both the Nanofraser Scholar and Nanofraser Explorer. Before starting using the software, I would like to give you an introduction to the Nanofraser and the Nanofraser technology, which will be the focus of this video. So before starting, I wanted to show you just briefly a video that we have published on our YouTube platform. It's Nanofraser on 2D materials, and from Heidelberg Instrument Channel we can have just a simple understanding of a very common use case of the Nanofraser, which is patterning on 2D materials, or at least the use on 3D materials. So we'll see the videos together. I'll comment it and explain to you the main steps of our technology. So first of all, we want to design, let's say, our contact pads. We want to make some connection of, for example, a molybdenum sulfide flake. So what we do is we go to our lab with our samples, and most likely we have our sample on a silicon sample and or any substrate. And first of all, we want to add the resist. The resist for lithography process is quite a common common name. For us, the resist is most of the time is PPA, because it's the best material for us for TSPL, thermal scanning probe lithography. So we spin coat resist, and we make sure that we have this layer of PPA on top of our flakes and on top of our sample. Secondly, we do an inspection of the flakes, because with the Nanofraser we're able to perform lithography, but we're also able to perform readings of any topography on a surface. So we want to first find the surface. So before actually setting up the tool, we have to insert our cantilever in the cantilever holder, and then insert the cantilever holder in the Nanofraser. In this case, we have a Nanofraser Explorer showing in the video. So the user is now putting the cantilever close to the surface, and now we are doing this reading procedure where we see the flake of 2D material which is being read. So we are identifying its position, and in this case we're not doing any lithography, any surface modification, just reading the surface in contact mode. So now, after we read, we place our design, and this is actually the following step, which is the patterning step. So here we're patterning the design that we have created previously. So here we created, and then we import it and pattern. So we pattern through the sublimation of the PPA material. After we pattern, we develop. So usually in this case we have a BLO sample, bilayer lift off. So we have to remove the under layer, which is usually PMMA-MA or PMGI, which is below the PPA layer on top. And to do this, we have this development step, which can be done in different solutions. And this is explained in our recipe book. Then, after we have opened our way through the substrate, we want to evaporate a metal, for example, to create contacts on our flakes. After we're done with our, let's say, gold evaporation, for example, we lift off the metal, which can be also done through the help of some tape in some cases, or with solutions. And then, after we're done, we inspect the final results on the optical microscope, and we see all our structure that we pattern with TSPL, and and the final result is quite satisfying, quite happy. So this is a very standard use case of the nanofraser. Now let's see a little bit more in detail what we are talking about when we talk about the nanofraser technology. So when we talk about nanofraser, first of all, we're talking about a nanolithography tool. So here I just put some examples of a typical microfabrication process. One very common is the etching, and another very common is the lift-off. In the video we just saw an example of a lift-off. What's common is that in the lift-off processes, usually we want to deposit some structures on top of the surface, and this usually happens through a metal deposition. While in the case of the etching, we want to remove materials. So for example, we use a reactive ion etching to remove some structures, and the lithography provides us this masked region where we don't want to remove some specific materials. Some information about us, about Heidelberg Instruments and Heidelberg Instruments Nano AG. So the nanofraser is a tool that was commercial since 2014. In that year, the company that made the nanofraser was called the Swiss Litho AG. The nanofraser was born with a collaboration with IBM and some researchers at ETH in Zurich, and originated from a previous project called IBM Millipede project, which was designed to create memory devices. But after flash memory devices came to birth, basically this project stopped continuing, but people kept on working on these special cantilevers with writing capabilities, and then they came up with the idea of the nanofraser. So not using an array of thousands of cantilevers to write memory, to make memory devices, but cantilevers to do thermal scanning probe lithography. So first tools were sold around 2014, and then in 2018 Swiss Litho joined Heidelberg Instruments, and we're now called Heidelberg Instruments Nano. Okay, so we're our branch in Zurich in Switzerland, and right now we're around 25 employees in Zurich that work and focus only on the nanofraser technology. Right now the main products that we sell are the nanofraser Scholar, which is a tabletop version, and the nanofraser Explorer. Actually, now also the nanofraser Explorer can be more tabletop, and both models can also be put inside glove box for special applications. So let's now see a little bit more into detail the nanofraser technology. We have key ingredients in this technology, which we see in this slide. So first of all, heatable cantilever tips, then thermally sensitive resist, PPA, and the closed loop operation. So let's see these ingredients in detail. First of all, the cantilever. So when we write with our nanofraser tool, we use special cantilevers, which are quite similar to the AFM cantilevers, standard cantilevers, but with the difference that they have a resistor around this area of the cantilever, which allows us to heat up the tip. And we also have another resistor around here, which is the reader resistor, which we call topography sensor. There are ultra sharp tip that can reach a radius down to 2 nanometers, and we have an integrated actuation through a capacitive platform. And in general, the final limit of the resolution of this kind of lithography is determined by the shape of the tip, because we can hardly pattern something that's smaller than the diameter of the tip at its apex, as you may also intuitively think. So this is our cantilever, a very important ingredient to our technology. The second ingredient is the PPA, the thermally sensitive resist. So our resist is called PPA, polyphthalaldehyde, and it's a polymer that decomposes upon heating by the tip into small volatile molecules. So we remove the material by sublimation, and the tip is being heated up by this resistance, which we call the resistance of the writer, and then the polymer is decomposed by this heat trigger. So this reaction, which is nicely endothermic, which is very good for us because we don't want heat to spread, and we want to keep the highest resolution possible when we are dealing with lithography. And this also avoids proximity corrections, which are common corrections that are implemented, for example, in some electron beam lithography tools. Another important ingredient to the technology, to the working principle of the nanofraser, is the closed loop operation. So how does our tool works? How does our scanning work? First of all, when we pattern, let's say we want to make any topography, we have a forward or trace direction, which is a patterning topography process. So we heat up the tip and we remove material, we sublimate it. Then when we come back, we are in contact with the surface, but we do not heat up the tip and we do not remove any material. We are reading, so we are imaging the surface. And this is going to be explained in the next slide, but it's a very powerful concept. Let's see now more in detail the cantilevers. So these are some information I'd already mentioned. We are dealing with a cantilever with a topography sensor, so what we call a reader, and a writer heater, which we call writer again. And this heats up the tip that you can see in this SEM image. And lastly, we have this capacitive platform, which allows us to bend the cantilever, because we have a bending by applying a potential difference between the cantilever and the substrate. Here you see some images of the tip, some SEM images, and then a TEM image of a very sharp tip with a radius below 2 nanometers, and also an image with a glowing tip of the heater. So when we heat up a lot this resistance, this will shine in the darkness, which is also quite cool. And these cantilevers are made of silicon, and they're developed originally at IBM and now are manufactured in MEMS Foundry. So, as we mentioned, ultra sharp tips. We have a tip heater which allows us to reach from room temperature to 1100, but even a higher temperature with very high resolution and a very good thermal time constant. We have an integrated actuation and a topography or distance sensors with very high resolution up to below 0.5 nanometers and Z-axis. So this image may allow you to see better in 3D the cantilevers we're dealing with, and also we can see a little bit more clearly this electrostatic actuation, which I mentioned earlier. So how we bend the cantilever is by applying a potential difference between this capacitive platform and the substrate onto which we are patterning. So I hope this review will help you have a better idea of the model of our cantilevers. Let's now see this closed loop lithography concept a little bit more in detail. We have a very nice video which I would like to show you, but first let's see more specifically, more in detail, this small scheme. So every time we make a line, so we move forward and backward, we have these processes. First we pattern one line with a hot tip, we remove the PPA, then we cool down the tip in a few microseconds, and then we come back and we image the topography of the written lines. So this is step 3, and tip is cold. We are in contact mode, and then when we are reached the end of this line, we use a feedback algorithm to adapt the patterning, and we pattern the next line. And this is a very important concept because we can use a feedback and we have a live view of our patterning, which is a very nice feature of the NanoFrazor technology. So let's now see this video which shows how the closed loop lithography principle works. So we have an input layout, as you can see here, it's a grayscale lithography, and we have an output image which is similar to an AFM image, but it's not an AFM image because it's collected by the NanoFrazor, and the principle behind the reading is different from the AFM reading principle. So we're talking about two different technologies. So let's see how this will work. So we input our layouts and we do the first line, we pattern, and when we come back we read it. And we do the second line. When we are dealing with darker pixels, we pattern deeper, and white pixels we do not pattern. And then we read the line. And during every line read, if we are using the feedback, this feedback can adapt and then optimize the force parameters that bend our cantilever to match the target topography with the measured topography. So this is a very powerful tool. So in general, we say that what we see is what you get, and we are seeing immediately what we are doing. So no separate metrology is necessary after lithography step. And in general, this closed loop lithography allows us an adaptation of the patterning every few milliseconds, and because of the feedback system, and this overall decreases the total fabrication time and increases also the accuracy and the reliability of the NanoFrazor. Some important parameters that we can change when patterning are reporting in the slides. You see that we can change the temperature at which that we have in the resistance of the writer that heats up the tip. We can change the force or the voltage that bends our cantilever. We can change the forward height, the distance between the tip and the surface, the contact time, which is the time that we spend in contact with the surface during each pixel, and also the pixel size or the pixel distance. So this is just to give you an idea that we can play with many parameters when we do the thermal scanning probe lithography, TSPL. And during the videos regarding the use of the NanoFrazor, the use of the NanoFrazor software, we will see also these parameters more in detail, how we can change them to control our pattern and to optimize our pattern quality. Another important concept in the NanoFrazor technology is the direct laser sublimation. So for the NanoFrazor Explore models, it's possible to also use the laser to sublimate material. In this case, the concept behind the lithography is the same. So we're using the same PPA resist, and the laser, similarly to the tip, is sublimating the PPA. But the spot of the laser is much larger than the dimension of the tip at its apex. We're talking about 500-600 nanometers. So we have the advantage of patterning much larger areas in a much shorter time. So in general, we have a sub-micrometer resolution possible, and we have a higher speed. Usually we have a higher laser dose required for usual photoresist exposure, and we can have a throughput of around 100,000 square micrometers per minute with a 150 milliwatt laser power at 405 nanometers. And yeah, 405 nanometers is a typical wavelength of the laser that we use with a nanofraser. So the laser allows us to pattern much larger areas much faster, so it's intuitive to think that we can integrate with the same resist and the same tool these two different let's say technologies, a laser and a TSPL, and it is what we call the mix and match lithography. So we use the advantages of the DLS module with the TSPL. So with the same tool, one software and same resist layer, we have a lithography step. We have 100x increase in throughput for micro features compared to tip only when we use the laser. And we also have an accurate alignment between the laser fields and the tip or TSPL fields, because we're able to read with our nanofraser cantilevers. And we can also directly inspect the laser patterns with the nanofraser, because we can do a closed loop lithography, so writing and reading, but we can also just do a reading with our nanofraser without damaging our surface. And you can see here on the bottom left a typical import of a layout in the nanofraser software. So we expect to make these large areas with the laser, and then these lines, as they get smaller and smaller, we typically do the smaller parts with the tip, so a thermal scanning probe. And on the right, you can see this image, which was collected using the nanofraser in a reading mode, and we did this small pattern with which is in the range of, we don't have a scale here, but it's in the range of 3 to 5 microns, while the bigger Heidelberg Instruments logo has a total dimension of around 40 microns. So this is it for the small introduction of the nanofraser technology. In the next set of videos, we will move towards the use of the nanofraser tool, the software. We'll see how to mount the cantilever on our nanofraser, how to start the software, how to change different parameters to optimize our patterning, and also some advanced functionalities that hopefully will help you in your experience with the nanofraser.